so much for being here, and thank you for coming. I know it's very late where you guys are, and I'm taking away from the ski slopes. Yeah, so thank you to the organizers for the invitation. I'm sorry I can't be there in person. So what I want to tell you about today is essentially a story about this Carlsson-Mellit algebra. And how to turn it from algebra to pictures, right, to skein theory. So this is everything I'm going to tell you about is joint work with Matt Hogenkamp. And so before I tell you what this algebra is, let me give you a little bit of context and maybe a little bit of history. So our main player is going to be this algebra known as AQT, right? So AQT is just the Carlsson-Mellit algebra. We're going to use that terminology interchangeably. And what we have is that the motivation for this, the original place where it arose, is in a combinatorics conjecture known as the Shuffle Conjecture. And what this conjecture told us is that the space of diagonal harmonics, if you compute its Frobenius characteristic, this was supposed to be given by some very explicit combinatorial formula in terms of parking functions and big paths. And for those of you, because I realize this isn't a combinatorics audience, the space of diagonal harmonics we can think of as really just the space down here. So it's just polynomials in two n variables, so n x's and n y's, whose partial derivatives are all 0, right? And so why is this? Well, I mean, this was interesting to combinatorialists partly because of the explicit formula that they're actually getting. So just to state the actual explicit formula here. So the conjecture was originally due to Hagelin, Heyman, Remla, and Ulyanov, and what they said is that this Frobenius character, right, on this side, well, it was already known to be given by this operator nabla en. I'll discuss that in a second. And what they said is, oh, it's supposed to be this big sum in terms of combinatorial statistics, parking functions, monomials, some combinatorial statement, right? Now, part of the reason that this is very interesting is because it gives you a formula for the action of this operator known as the nabla operator, which again, if you're at all involved or have heard of Qt-Catalan functions or Qt-Catalan combinatorics and a lot of its connections more recently to, well, homology theories, right? This is due to, Gorski and Bazarani and obviously Hogenkamp. A lot of work has been has related this operator and to this area, and so this is part of the reason why you might care about it. In any case, this conjecture laid open for 14 years, and it was finally proven by Carlsson and Mellit. So really, I should write theorem here, not conjecture. This is a theorem. I'm sorry. And the way that they proved it was not by appealing to traditional combinatorial means, which is how people were trying to prove it for many years, but by introducing a new algebra, which they called AQT. And defining a representation of this algebra over these spaces that we're going to call Vn, which are really just going to be essentially the ring of symmetric functions. That's what this is in infinitely many variables. Sorry. The ring of symmetric functions with infinitely many variables and some additional variables y1 through yn. And I should mention, because this will be relevant at the end of the talk, that there is a rational generalization of this known as the rational shuffle conjecture, where instead of taking the action of the nabla operator, there's another operator that shows up. And here, these dig paths, I should say, these are essentially lattice paths on an n by n grid. Right, they're just little lattice paths on an n by n grid. You can generalize this to n by m, and there was a rational generalization of that. This was proven due to Mellit, and it was proven, in essence, in a very similar way by again defining a different representation of AQT, but again over the same vector space, and we'll be discussing that as well. So, combinatorics aside, why might you care about this? Also, if you have any questions at any point, please interrupt me. I can't keep track of the chat if you have questions. So just speak up. All right, so combinatorics aside, why might you care about this? So maybe a bigger worldview of this algebra is the following. So one of the things that in the recent years has caused a lot of really amazing research have been these conjectures known as the GNR conjectures, right? The Gorski-Nabitz-Rasmussen conjectures, which in essence tell you something about the homology of, algebraic knots and links from Zergo bimodules to Hilbert schemes, right? They tell you about the Kavanagh-Wierzbowski homology of these things. But one of the things that this world doesn't just relate Zergo bimodules with Hilbert schemes, as I mentioned previously. One of the things it's done is it's related a lot of these formulas and a lot of these polynomials that you get out of this to algebraic combinatorics through QT Catalan numbers. It's also obviously related to the Daha and Trednik algebras, which in turn is related to elliptic algebras. And you have this plethora of ideas and worlds are kind of interacting together through different sides of the same coin in some sense. And what seems to be showing up in a lot of these places is this algebra AQT. And this is part of the reason why I originally came to it. I'm like, oh, this is actually very interesting, because not only is it related to this kind of combinatorics picture, which is the original motivation, it was actually, so this is work of Eugene Dvorsky and Carlsson-Mellit shortly thereafter. The original proof came out that you can realize AQT and its representation using parabolic like Hilbert scheme. So there's a geometric interpretation of a lot of this context, right? AQT in some sense contains the elliptical algebra. This is work of Mellit. Its representation, again, which I'm going to tell you a little bit a lot more about in a second, can actually is related to a certain stable limit of representation of the Daha, right? And then when looking at this, Matt and I, right, we thought, well, wouldn't it be nice if AQT was in some sense related to Zergo bimodules? It seems like there should be a natural link. And this is where categorification and the story that I'm going to tell you about today, which is really the scheme theory underlying all of this, comes into play. So again, this is just context and worldview so that you understand, if you've never heard of this algebra, why it seems like a natural thing to study. All right, so let me actually tell you what it is. And I apologize, I don't know what, the air is very dry or something, so I'm going to be drinking a lot of water. Okay, now, so what is the AQT algebra? So like I said, this is something that was originally defined by Carlsson and Mellit, and we can think of it as just an algebra over QQT with a family of idempotents. We're going to call them 1n, idempotents indexed by integers, and certain generators, Ti, D minus, D plus, and D plus star, which we can think of really just endomorphisms in some sense of objects n, right? They're just operators that jump from one point to another. So in some sense, this is just a quiver, right? And in addition to these operators, we want to think of D minus and D plus pointedly as raising and lowering operators, right? The reason for that being that, again, if you look at this picture and you think of the idempotents as being the points in this quiver, the D pluses go up, and really these are also the D plus stars would take us up, the D minuses take us down, the TIs stay local. And then we have two extra families of operators that we can define. We can define these phees, which are really just the commutators of D plus and D minus. And we can define certain polynomial generators. I'll speak more about these in a second, which are really just kind of rescalings of these phees. We're going to denote those by yi and yi star. Okay, so here's the definition. It's some algebra. Yes.
Maybe I do this, but so do D plus star and D plus commuter. So what is there a relation?
So I'm going to tell you the relations. Okay. Yeah, no. There's a lot of relations. Very few things here. Some things commute, but not all. So here's the generators. And now what are the relations? Excellent. So there's a lot of relations, right? And so the TIs, you want to think about these as basically just a copy of the Heck algebra. They're just generating a Heck algebra. You have some operators commuting. So the D minus, oh, this should be a D plus, sorry. The D minus and the D plus commute sort of with the T's, but not always. You have another family that we like to call the Braid absorption relations. And really, these relations, even if they look a little strange, if you're familiar with double affine Heck algebras or Dahas, they're analogous relations, right? Not all of them. So the AQT is not the Daha, it's different, but a lot of the relations are very much the same. And so there's, you know, if you've never seen it, it looks like a lot of weird relations, but they're, again, very algebraically, very nicely motivated. In addition, so all these relations you'll notice are just given for operators that don't have stars, right? And remember that I told you that we have, let me rewrite the generators here just so you remember them. We have TIs, we have D plus and D plus star. We have D minus. We have phi and phi star and YI and YI star. Right, and these relations here, none of these operators have stars. And the reason for that is that there's a natural map, in some sense, internal to the algebra, which I'll talk about in a second again, that allows us to notice that there's a complete symmetry. So the relations that hold for the unstarred operators are the same as the ones that hold for the starred operators. So everything here, you have actually twice as many relations, because for everything here, you
very small thing. I mean, sorry for being picky, but on the
no,
fourth line,
100%.
is there a square missing? Maybe on the fourth line, the first TID plus square is equal to TQ Q inverse D plus square. No?
Am I missing a square on which line?
Fourth line, the fourth.
Yes, 100%. Of course. He's. Thank you. Yes. Thank you. 100%. Okay, great. So we have these relations.
Sorry, but
Is there a question?
It's T1 D plus square, not Ti D plus.
Yes, as well. Thank you. Here, thank you. Yeah. This is the Tn minus 1 and this is the T1. Thanks. This is the problem with doing handwritten slides. Lots and lots of human error. All right, and then in addition, we have these intertwining relations, right, that allow us to essentially mix these two copies, right, the starred and the unstarred operators, and they tell us how they interact with each other. And now, one of the things that I mentioned was that we also have these additional operators, right, Yi and Yi star, these polynomial generators. And the reason I called them a polynomial generator is because the Yi's commute with themselves. And in particular, if you just look at the subpiece generated by Y or Ti together, they generate an affine Heck algebra, right? And so in some sense, this is why I compared it to the Daha naturally. What you really have here are two copies of the affine Heck algebra, right? The ones generated by Yi, the one and Ti, and Yi star and Ti inverse, with some additional raising and lowering operators. So these are the D plus star, and D minus mixed together in an interesting way. All right, but I want to point out that the way that they're glued together is not the way that the Daha, which again is also formed by taking two copies of the affine Heck algebra and kind of gluing them together. They're not glued in the same way. So that's just, again, kind of to put it in a framework. So you have all these wonderful relations. And what can you do with this algebra? Well, what Carlsson-Mellit did, the first thing is that they defined a representation of this algebra, which turned out to be very useful. And to do so, they defined the following vector space, right? So as I said in the beginning, we're going to consider basically just the ring of symmetric functions with some additional parameters tensored with, y1 through yn. And notice that when you set n equal to 0, you really do just recover the usual ring of symmetric functions because you don't have any y's. And we're going to think about this vector space as being graded. We're going to think about this vector space as having a grading by n, right? Which is just well, the number of y's, and m being the homogeneous degree of the x's. So this is just the usual grading that you would put on the ring of symmetric functions. And with that in hand, we're going to define an action of AQT, where we're going to, again, think of d plus and d minus as being raising operators and lowering operators, right? So they take us from n to n plus 1, or n to n minus 1. And then these operators as being endomorphisms of it, right? So they're going to preserve the n. Right, so in this representation, if you still remember that we had these idempotents, what we're really doing is we're sending each idempotent n to Vn. That's kind of what's happening here. Okay, so how does it actually act? What's the actual representation or the actual action? So there's multiple, right? And this is where I told you at the beginning that there was the classical shuffle theorem, but then there's this rational generalization that was proven later by Mellit. So for the classical shuffle theorem, the one that you involve nabla, this very interesting operator, Carlsson and Mellit defined the following action. So they said, all right, we're going to define y. Question? No. Okay. So we're going to define yi to basically just be multiplication by the parameter or the variable yi. That makes sense. Ti to be this very classically known de Moivre-Lustig operator, right? So this gives you in the polynomial representation of the affine Aqt algebra. And then they defined these 3 additional operators to be, again, if you're not a combinatorialist, something that looks a little bit potentially scary, right? So let me just break it up. Here, this is what's known as plethystic notation. And it's basically just, and you know, if you're a combinatorialist, you're probably screaming at me, but this is really just a way of including an extra variable into your alphabet. It's basically saying take a function that only depends on x's and find a way of including an extra variable y in your alphabet. So now f depends on y. And there's a formal way of doing this. This is really just taking the residue in the usual complex analysis sense. And so here you're basically taking all these plethystic operations, conjugating by t's, and here conjugating, or not conjugating, what am I saying? Composing, sorry. Composing by a map that basically permutes, or not permutes, yeah, rotates the y's, right? Sends yk to yk plus 1, yn to y1, etc. Well, with multiplication by q, but all right, so here's the action. We're not going to care too much about the algebraic action. The point is that it exists. That's really all I wanted to get at it, because what we're going to do later on very shortly is translate all of this to diagrams. So we're not going to actually care about what the explicit plethystic notation or the plethystic operation was. But let me very briefly point out that there is a second action that was later on described by Mellit, which in some sense is a modification of the first action. And what Mellit did is he changed the action of d minus and d plus, right? By saying, all right, let d minus, rather than being the residue at yn, let it be the residue of the constant term. And then let me modify d plus by incorporating an extra yn variable here. All right, yn plus 1. And these modifications don't seem, you know, particularly enlightening if you're haven't worked with this. But what's amazing about this is that this second modification allows you to recover the first action from the second one, right? Through essentially the following formulas. But more amazingly is that you can actually use this second action to, in some sense, construct or replicate or to construct an infinite number of actions, right? And for each of these new actions, they're indexed by essentially a lattice point of pairs that are co-prime, right? And this is where you end up getting this, in some sense, elliptic Hall algebra showing up that I mentioned at the beginning, right? And so moral of the story, from this very, very important action, you can generate an infinite number of them. which is amazing. Okay, great. So now what I'm going to tell you, and this is most of the content of the talk, is how to turn all of this story to skein theory and how potentially we can find this helpful. So any questions, because at this point I'm totally gonna stop talking about combinatorics and actually draw you some pictures. The first part's a little dry. I understand that it's a lot of like background theory, so thank you for your patience. All right, no questions. So let me move on. Oh, shoot, I forgot one thing. I was about to move on and then I realized I forgot something. Hold on, sorry. So one of the things that's very, very important, and I absolutely need to mention this, is that recall that the whole point of them introducing this action was so that they can compute what this nabla en operator was, right? And so the question really that we need to ask also in order to have a complete picture is, how does nabla show up in AQT? And so to do that, Anton and Eric, or Carlsson-Mellit, sorry, what they did is they introduced an involution on this vector space, which they called N, right? Which essentially recovered the action of nabla at the symmetric function level, but raised it higher, right? To like V1 and V2 and V3, et cetera. So in some sense, it generalized what nabla did, but on all these higher level vector spaces. But what's interesting about it is that not only does it really recover nabla, it also intertwines the actions of AQT, right? And this is what I was trying to get at earlier, where I said there's a symmetry between the starred and the unstarred operators that are showing up. And the reason is because the involution N is really conjugating one of the actions to get the other, right? And we see that exactly here in these relations that tell us how do you go from half of the algebra to the other half? Well, just by conjugating by N. And so this is also a crucial part of the story. Okay, now I'm ready to move on. So let's talk about the Aqt algebra. But first a water break, sorry. All right, so this is fairly classical, hopefully. So to us, the Aqt algebra is just going to be the QQT algebra generated by, well, obviously, this is very classical, right? The generator is Ti modulo the Braid relations, and then this additional relation. And so by assigning to every Ti a positive crossing, a Ti inverse, a negative crossing, we can obviously interpret all of these relations as just pictures, where the classical Aqt algebra relation just becomes the skein relation, right? And so this allows us to assign to every element in the Aqt algebra essentially a braid. Okay, and so going from here, what we want to do is say, all right, how can we construct Vn from this, right? That's really what our goal is. So we know, based on the previous slide, that that means that Hn is really just the span of diagrams, in particular, braids mod the skein relation, right? One of the things that we can do on the Aqt algebra is we can act. We can act on the left and we can act on the right by itself. And so we can ask, well, how does that translate to diagrams? Well, the left action and the right action are just conjugation by diagrams on the top and on the bottom, right? So in particular, if we think about taking the cocenter, right, if we quotient by the set of all commutators, that's analogous to saying that the right action and the left action are the same. So it just corresponds to taking our diagrams and essentially closing them around a thickened annulus, right? And so that allows us to see immediately that this cocenter is really just the span of Braid diagrams mod skein closed around an annulus. But here the question still remains, how do we actually incorporate the y's, right? So recall that we have this beautiful theorem of Turaev and Aston and Morton, and I'm possibly missing a few people here, that tells us that if we actually take the direct sum of all these cocenters, we recover the ring of symmetric functions, right? Where here, multiplication of symmetric functions just corresponds to basically filling the donut in some sense, right? You take your annulus and you stuff a donut inside it, or you stuff the annulus inside it. And this gives us the multiplication structure. Right. So in order to incorporate the y's, what we want to do is to think about taking our Braid diagrams, but not necessarily closing them entirely, but taking a partial closure, right? Taking partial cocenters if you would like. And what we end up with is precisely an isomorphism between these partial cocenters and diagrams like this, right? Where we're, again, taking our certain number of strands, we're allowing any diagram, but then we're only closing a finite number of them on the right. And once you have this at hand, you can actually show very, very easily that this vector space Vn, right, which is, again, the ring of symmetric functions tensored with variables y1 through yn, can be obtained by just the following construction, taking diagrams exactly of this form, right? You have braids where you close m of them, but you allow the diagrams to be any braids with the additional condition that if you essentially, if you act on the bottom, the action on the bottom is trivial, right? And that's equivalent to saying that if you have any crossings on the bottom, they just get absorbed, or that secretly every diagram has a young idempotent at the bottom, right? Yeah, I don't know, any questions about this, about the actual construction? Is everybody totally lost, or is it very easy? All right, no questions. I'm hoping that just means everybody's following along and I'm just boring you. That's better. Okay, so with this construction at hand, the next question that you want to ask is, well, how do we actually recover the action? We have the vector space. How do we define pictures on top of this? And so we're going to define the following operators. We're going to let D be just diagrams in this vector space, Vn, right? And we're going to define the action of Ti, right, the zero the Aqt algebra operators to just be, well, you take the ith strand and you cross it past the ith plus first strand. We're going to let D minus, remember that this was our lowering operator. Well, what is it going to do? It's going to take your ith strand, or sorry, your nth strand, and just wrap it around. And remember that D minus, let's just do a little sanity check, is supposed to go from Vn to Vn minus 1. All right, and that makes sense. It started off taking an input of n strands, and at the end, the output is something that has only n minus 1 strands. So that makes sense. Right, and if we continue in this way, we can go ahead and essentially check all of these. All right, so what is D plus? D plus is going to be, you take your original diagram, you have to add a strand because you want to go from Vn to Vn plus 1. So you add a strand. But remember that one of the properties of being in this vector space is that you have to be able to absorb crossings on the bottom, right? And so to do that, you basically just glue a multiple of your Young symmetrizer or your idempotent on the bottom, and therefore any crossing gets absorbed. Yi, you can construct from the commutator of D minus and D plus, right? But that's basically just going to be, you take your ith strand, you wrap it around, and you bring it back to position I. You have phi, which is actually the commutator of D minus and D plus, where you take your nth strand and you wrap it around and you bring it back to position 1, etc. And you can do this for the start operators as well, right? You can define these things as you see in the pictures, right? And so if you remember the original action that was given combinatorially, if you're not horrified, or if you're not a combinatorialist and you're a little bit scared when you see this pluralistic notation, these diagrams are a little bit more user-friendly, at least at the very beginning. Yes, any questions though? Are the pictures making sense? Yeah. Okay. And so then with that in hand, we have our first theorem, which is that these diagrams really do induce a topological action of AQT on this vector space that realizes the polynomial representation of Carlsson-Mellit, right? This first action that I talked about. And really, I should point out that this is when we specialize T at -1, right?
I have a question regarding the previous slide.
Yes.
So I was wondering, so you see, I mean, many people, and I should say, including me, like this other presentation of the Aqt algebra, where you see this trivalent edge instead of crossings. So is there some kind of renormalization of your generator to actually, instead of having some topology, to have some planar but trivalent things? Or
Sorry, so how do you like to draw the crossings?
no, I would like to get rid of the crossings. That's my point. To put some.
I see.
So is there any canonical basis for the algebra? As understood, like,
Sorry, let me answer Louis' question first. So the answer is not that I'm aware of. I don't have pictures for it that don't involve crossings. So and that's in some sense intentional, because our goal for this was to categorify it later on.
Yeah, so I get that, but that's okay. So
yeah,
I mean,
no, to answer your question, I don't have it. No.
Okay, thank you.
Yeah. So totally. And sorry, there was another question about if there's a canonical basis for this.
yeah, it was a reformulation of the first question.
Okay, I see. Yeah, no, so I don't have any, no, not that I have. Maybe Anton does, if Anton's in the audience somewhere.
Yeah, I'll ask him.
Thank you.
Yeah. Okay, so what is the point is that this realizes this really does give us the action. And just to clarify, if you're familiar with this algebra before, if you look at the source paper, their normalizations and our normalizations are a little bit different. Their T's and our T's are not the same. Their Q's and our Q's are not the same. So when I say at T equals Q, that corresponds to T equals Q inverse in their normalization. So that, if you're trying to piece things together. All right, and the proof for this is obviously, as you would expect, entirely diagrammatic. There's, you just do it, which is pretty awesome. Okay, so what about nabla though? This involution that's supposed to recover the n, which is supposed to recover the operator nabla, this involution that's supposed to conjugate the starred and the unstarred operators. Well, that becomes the very, very natural just composition with a full twist operator. All right. Well, plus changing positive and negative crossings with each other, but that's to be expected. Right. And so n is really just, in some sense, the most natural operator you could expect, right? So maybe, should I do an example? Yeah, why not? All right, so just to clarify, so n, you feed it a picture, you change all the positive crossings to negative crossings, you change Q and T to Q and T inverse, and then you compose it with a full twist. All right, so how would such a computation look? Well, you're a topologist, so I don't think I have to explain this, but just in case, right, we're supposed to be getting that the starred operators come out naturally from the unstarred operators just by conjugation by n. And in fact, if you go through and you compute it, you get exactly that, right? Because whenever you apply the second n, you're supposed to change every positive crossing to every negative crossing, the full twist becomes the full twist inverse, and you get beautiful cancellations going through. And so really everything works out exactly as you would expect. Okay, so one of the things that I also mentioned at the beginning of the talk was there is this second action due to Mellit, where he allows you to not only recover this Carlsson and Mellit action, the first action that I've talked at length about already, but he also has a process where you can take this action and generate an infinite number of actions, right? Indexed by points on a lattice. And so there's a natural question of, well, can we realize this action as well topologically? And the answer is yes, but we have to be a little bit more careful. And to do that, we're going to modify the description of the Aqt algebra to not only include upward pointing strands, but to include locally downward pointing strands, right? Which is to say, we want diagrams that still, at the boundary are just upward pointing, but somewhere in the middle, we're going to allow things that potentially point downward. And one of the things that we get, and I have to describe this obviously, is that the Aqt algebra can actually be recovered in exactly the same way, where you consider diagrams, more general diagrams like this, but you don't only have the relations of skein and isotopy, you also have to include what we're going to call the Heisenberg relations, right? And so what are these Heisenberg relations that we need to impose on these diagrams to make this equality true? And so the relations are the following. So we're going to say that whenever we have a right twist, left twist curl with a negative crossing, that's going to be a 0. Whenever we have a positive crossing, we're going to end up with just a multiple of essentially the identity. A bubble is going to evaluate to just the empty diagram with some constant, right? And then we have here that depending on the orientation of your crossings, sometimes they can be undone and sometimes they can't, essentially. So if you're familiar with Heisenberg algebras, again, this is precisely the relations that you would expect in a Heisenberg relation. These are a little bit degenerate here, I should point out. These look a little bit degenerate, but that's okay. So they look a little bit weird. The point is that once you have this Aqt algebra that allows you to have more general diagrams, things that are potentially pointing downward, and then using the same process as before, right? We can still consider partially closing the diagrams. We can still consider, having this condition of the idempotent on the bottom being there, or the action on the bottom being trivial, however you would like to think about this. And so that allows us to think of Vn as, again, the span of these more general diagrams where you have locally downward pointing arrows, modulo all these relations, Heisenberg's gain, and Braid relations, with the additional relation that if you ever have a downward pointing strand near the puncture, right? So if we think of this as the puncture and this is just a downward pointing strand, then that's automatically going to be 0. So you can't have downward pointing strands immediately in the vicinity of the puncture. Okay. Yes.
With this relation, so I mean, I had the feeling, I had the impression, but I was wrong as in the beginning, that everything was kind of upward oriented, but I was wrong. But when you impose this relation, does this, so do you kind of kill every diagram which has some kind of downwarding, I mean, some kind of orientation which doesn't fit, say, well, I guess in your examples it would be the clockwise orientation.
Do I kill any diagram that has the clockwise orientation?
The anti-qua, so which is not, sorry. So I'm not being clear. So it seems to me that you kill a lot of things which contain some orientation which are not clockwise, yeah? So
yeah, so yeah.
So does it kill everything which is not clockwise?
The top relation is not clockwise, right?
Yeah. I don't think so.
That's not 0, that's empty. The top bubble.
Yeah. Yeah, that's true. Okay. Well, okay. So sorry for being stupid.
No. It's also just hard without like you drawing what you mean to do it. Like, I'm like, what do you mean? This or that? Okay, sure. Thanks, Josh. I think it was Josh who pitched in. All right. So once you have these relations, you have an alternate description of Vn. And then what we're going to do now is basically modify the action. Or not, sorry, describe the action directly. So this in hand, we can define these new operators. We're going to call them d minus Mellit and d plus Mellit, right? Again, because these are the second action defined by Mellit, where our d minus now is going to take your nth strand and it's going to go downward. And one of the things that, and I'm happy to slide back if you would like to see them again, but one of the things you can check is that in the original action that I defined previously, every diagram at any given point, the arrows were always pointing upward. You never had anything that went back. You never had anything that was locally downward. But here, because we're expanding our vector space, this is totally fine. right? And then D plus becomes something that's a little bit more complicated. So this is still oriented totally fine. And what's amazing is that not only, right, and this is, I guess, the theorem at the end, is that not only do these diagrams really give us Mellit's action, the second action, they also, through the exact same recipe as Mellit, obviously, allow us to construct an infinite number of topological actions, where you can actually recover M and N as precisely the slopes of the diagrams that you can think of as living on this punctured annulus, right? Or a punctured torus, whatever. Where you're going to have, if you have a diagram, let's say this is kind of the space that they're living in, we can think of one of the slopes as being how many times you're going around in this direction, and the other slope is how many times you're going around in this direction. And you can see that exactly in the diagrams that you're getting, right? Yeah. And so, all right, where do we go from here? So I ended a little bit early because I either went too fast or nobody asked questions, not too many, but that's okay. So maybe future directions. So one of the things that you, depending on your interest, would like to or can investigate using this are potentially new operators on the ring of symmetric functions, right? You have a plethora of drawings that you could draw, right? Maybe they're not necessarily easy to express algebraically, but they make sense topologically, and you can ask, well, is this going to give us some interesting constructions? There's a lot of connections between, like I mentioned at the beginning, QT combinatorics and knot homology. And one of the things that this construction allows us to do is to actually explicitly draw what a lot of these symmetric functions are, what a lot of these operators showing up are, and potentially apply it to solving a lot of these or some of these conjectures that relate both of these worlds, right? And potentially more interesting, depending on who you are, is a categorical understanding of all of this, right? And this is something that we've been working on for a while now, but let me just say a couple of words on it, right? You'll notice that, oh, sorry, I left an eta here. This is not, I don't know why I wrote eta. This should be a TQ inverse. So you'll notice that one of the things that I left in all of these diagrams was precisely a T and a Q, right? Even though I said, oh, really secretly, I'm specializing T to -1. And the reason is that you can interpret all of these pictures, as I mentioned briefly to Louis, in terms of circle bimodules, right? They're diagrams. You can take a crossing and just lift it to a chain conflict. So all of these diagrams have a natural interpretation as certain complexes of circle bimodules, which means that the operators on them correspond to certain functors. So there's an analogous construction for all of this, an analogous categorical construction for all of this that doesn't, where, you know, this T equals -1 construction is really just showing up because in some sense the skein theory that I'm showing you is just a decategorification of this, you know, higher categorical setting. So that's where the T equals -1 is or why it's showing up in this context. Yeah, and so our hope is that using this much more categorical understanding, we can actually use the operators to, well, to do something cool. Let me just say that. Cool. All right, that's it. I'm ending a little early, Louis. Hopefully that's okay.
Yeah, sure. I mean, German should answer.
Okay.
Thank you.
Other question?
Maybe I have a question. I think of course, I think it's definitely possible to imagine a VN where you color strands with a kind of wedge or exterior powers of things. So my question is, does AQT would act on that in the same way? Do you need some extra to throw in some extra generators in relation to speak about colored diagrams, or is it just fine like this?
I don't know. I haven't thought about this. Probably not, but I don't want to speak because I haven't thought about this at all. Yeah. That's a good question. I don't know.
So maybe related, so I mean, that was kind of my feeling, and related to that, so do you think it will be this theory with color would be tackable somehow and would be kind of understandable, or would that make the whole business really more complicated?
I guess I don't, if I were like algebraically, what would that correspond to if I were to color the strands? You know, and I really am just thinking of this as like coloring the strands of Vn, presumably, right? It's just like, what would it mean to color the strands in?
Well, in terms of Sargo-Barmutos, it means that
Oh, you mean, yeah, sorry, of course, that makes more sense. I suppose you could do it. I don't know. I don't know. I would have to think a lot more about this. I don't know.
Well, okay, thank you.
Thank you, though. That's actually yeah, I'll think about that. That's a good suggestion.
I have an easier question. Can I ask? So,
Okay.
yes. So, if you have Vn, so let's just take V0. So we have just a bunch of strands going around, but there is no extra strands.
Yeah.
But if you allow this downward pointing things, like how big is V0 as an algebra? Like this should be the full skein of the annulus, basically, right? So
Hold on. If I'm allowing downward strands, but going around the puncture as well, or
yeah. I allow that, or you don't?
we're not allowing that at all.
Ah, I see. Okay.
We're not allowing that at all. No. So that's the whole point, right? It's like, that's why I started by saying, you take whatever diagram here, maybe you go up and down here, but everything here is up, and now you close it. So you only have the same, you always have the same orientation going around the puncture.
Okay. And so in particular, you can resolve all these things by kind of standard diagrams, and then the size of Vn doesn't change. Okay.
It doesn't change at all. It's exactly the same vector space. Yeah.
Okay. Because in principle, you can take a double kind of when you allow things going up and down.
Yeah, we've tried this and not
Okay.
succeeded.
Okay. Yeah, we should talk about this. That's fine.
Yeah.
Okay, other question? If not, then let's thank Nicole again.
Thank you so much.